Oh, yeah. And then I see this and I'm like, oh, my hair's a little wild today. All right, here we go. Oh, well, thanks. But it's a little windblown right now. So it does. It does. All right. I'm going to plug in my iPad just because it tends to get low and then just die. I don't want that to happen. All right. So plan for today is to just go through last year's exam because I am going to base this year's exam on this. So it's going to be important, you might see questions in a little bit of different order or things like that. So just highlighting. So you're going to see pretty much a page and a half of short answer qualitative stuff. And then we start getting into the quantitative stuff. So now we add a third part to the exam. So the first part is always the no partial credit. It's just kind of qualitative or single word answers. Then we start getting into some computational stuff. So there's going to be a few pages of this. And sometimes because we have so much data that we need to present the exams a little bit on the longer side in terms of the number of pages, but it's really not a longer exam. And then we're going to have a complex problem, which is either going to be equilibrium or rate. You get to pick one. So these are going to be ones you haven't seen them at all. It's not like it's going to be the same flavor of a problem where it's like I just changed the numbers, but you have to figure out, is it kinetics or equilibrium that you want to do for this, this extra problem. So let's just start at the beginning. Okay. Indicate whether the following would increase, decrease, or have no effect on reaction rate for a first order process that is irreversible. So it's important to highlight that we're not talking about equilibrium here. And so that's an important piece to highlight. And move, there we go, move me there. That this is an irreversible process. So that's an important piece when we're talking about rate, is highlighting that we're not talking about equilibrium. And so this is asking about reaction rate. So when we talk about decreasing the volume of the reaction, that's really not going to necessarily have any effect on reaction rate, or at least for what you guys have learned about. When we talked about changing volume of the reaction, that had to do with things with equilibria, where we could favor one side or the other. We really didn't talk about changing the volume of the reaction having any effect on reaction rate. Increasing concentration. So we can increase the concentration of the reactant, and then that will cause an increase in the reaction rate. Okay. Decreasing temperature of the reaction, that is going to decrease the reaction rate. Now that I'm looking at this problem, I might reword this a little bit because parts of this speak to an aspect of kinetics that we've actually moved into the second half of Gen Chem. So there's aspects of this that I might kind of speak to, but we might not see all of this here. Because I don't actually, as I'm going through this, I'm like, I don't think we talked about this stuff this semester. So this question might either be completely eliminated or be a different sort of flavor when we're talking about reaction rate. When you decrease the concentration of product, remember there's no kind of effect of products on reaction rate. That's only reactants. And then catalysts are things that increase. So I'm going to put a little note here. We're not to see the same types of questions because this a lot of these pieces we actually tabled for Gen Chem 2. So you're going to see a qualitative question on rate, but some of these things are not things that we've talked about. All right, now we've got some stuff that looks more like the stuff that we've talked about with regards to rate. Okay, and this is, here's a chemical equation, here's a rate law, answer some questions with it. Okay, so using the following information, what is the order with respect to A? And since you're here with me, Emma, and you asked for some extra help with kinetics, I'm going to put you on the spot. What is the order with respect to A? So it's first order. And we know that because there's an exponent of 1, which we don't really see there. Okay, remember, we do not look at the balanced chemical equation to tell us anything with respect to order. How about with B? First order as well. And if the question asked, what is the overall reaction order? Because I don't think it asks this here. What would you say? Second order. We add those exponents. So you add those exponents to get your overall reaction order. So now there's some qualitative questions asking about how concentration changes would affect things. So if we triple the concentration of A, what would happen to our reaction rate? We triple it. So here's how you'll handle these. What you're going to do is you're going to put a 3 in for here. Okay. And then because that's to the first power, that means my rate is going to increase by 3. Okay. So this is going to triple as well. And that's because it's first order. Okay. We essentially take 3 to the first power, and that's going to be equal to 3. Now, if it was second order with respect to A, then that tripling would be 9. Very good. Okay. So I'm going to erase this up here. If the concentration of B is doubled, what would be the expected increase in reaction rate? It would double as well. Now, let me ask a follow-up question. If I said if the concentration of B is halved, what would be the expected change in reaction rate? It's still first order with B. It would just be halved as well. When there is that first order relationship, it's the exact same thing. Double the concentration, double the rate. Triple the concentration, triple the rate. Halve the concentration, halve the rate. So notice here that because we have numbers that are greater than 1, I can talk about the increase in the reaction rate. Okay. Keep in mind that it's likely that you're going to see this wording be, what's the change in the reaction rate? Because if you decrease a concentration of something, you're going to slow the reaction down. If the concentration of A and B are both tripled, okay, what would be the reactant increase in the reaction rate? It's going to be 9. So what you want to do here is imagine taking rate equals what's the concentration change? So it's going to be 3-fold to the first power times 3-fold to the first power. So it's going to be 9-fold increase. Now, trick question, not really trick question, but another flavor of this. If I tripled the concentration of A, but I 1/3 the amount of B, what would be the effect on reaction rate? No change, right? Because it's 3 to the first power times 1/3 to the first power. Multiply them, they cancel each other out. Okay, so that's how you handle if you're evaluating rate changes with multiple things. What would you plot on the y-axis versus time on the x-axis to give us a straight line for this kind of reaction? So again, if we're talking about things with respect to the concentration or with respect to A, what would that line look like? Yep, it's going to be ln. Okay, and that's because it's first order. If we had this guy, do you know what, if we just had the reactant concentration, this one's going to be second order. 1 or over is going to be second order. I should write second. This is going to be 0. Yes. Okay. Okay. So you're going to see a question just like this, but obviously different starting equation potentially, and then different questions with it. Okay. Here's a question about equilibrium constants. So by looking at the equilibrium constant, state whether the equilibrium mixture would be composed of primarily reactants or products. And how do you know that? Mm-hmm. Very good. So that's because that's a small number. Okay. And this is actually a really important equation because it sort of leads us into what our next learning unit is going to be on, which is acids and bases. And so we're going to start talking about strong acids and weak acids and so forth. And so this is going to be weak acid. We've actually already learned about these. We've learned about these COOH guys. These are the carboxylic acids. So these are weak acids. And weak acids don't make a lot of H3O plus in solution. But for any equation that you're given, we look at this like a number line. Small numbers lie on the left side of our number line. And so that favors reactants. Any questions on this first page?
Other than number one.
Yep. Yeah, as I was going through this, I was like, nope, we're not going to see a question like that. There are aspects of this that we sort of talked about, but we didn't talk about effects of volume, temperature, things like that. We didn't even talk about catalysts. So not likely to see something like that. Okay. All right. So consider this equilibrium system. So now you've got an equilibrium equation. How do I know, even if the prompt didn't say, how do I know I'm dealing with equilibrium? Right, we see two-way arrows, okay? And we learned this, we actually learned that term enthalpy. Do you know if this reaction generates heat, my delta H, is that going to be positive or negative if it generates heat? Right, very good. So you do want to know that. That's something we did learn about, okay? So if you see that delta H has a negative number, that means it's going to generate heat, which means we're going to write heat on the product side. And that's important because when we talk about how a reaction is affected by temperature, okay, we're going to see that we're going to treat heat as a reagent here. So now this question asks us, does the equilibrium position shift right or left as a result of the following disturbances? So what if we add C3H8? C3H8 is this guy. If we're adding it, we push to the other side.
Oh, shift right. I meant shift right. Yeah.
Yep, shift right.
I was thinking the right thing.
But your words came left and right. Yes. Okay. So we are removing water. Correct. Adding CO. Cooling a reaction. And when you see this word, reaction is cooled, we want to think about removing heat. If you say the reaction is heating, that means we're adding heat. So we need to treat heat. So we can think about removing heat. Very good. Yep. Pressure is increased. So how do we know, how do we figure this guy out?
I just remember the little graph bottom. So like with volume increases, the pressure.
So you're absolutely right. So volume is going to decrease. So we make a smaller space for our molecules to live. So we need to find the side of the equilibrium that has the fewest number of gas molecules. Okay. Do you see how many gas molecules are on the left? How many are on the left? 4. And how many are on the right? Right. We have to make sure we look at phases. So because there's fewer gas molecules on the left side and we've made our space smaller, that's where our equilibrium wants to live. So we are going to shift to the left. Okay. So look back at your quizzes too, to see if there was any other, because basically too, when I make these exams, I look back at old exams and then I also look back at old quizzes and I say, do I have a representative problem from those things? Because each quiz is 25 minutes. the exam, and all of our quizzes, we have 2-unit quizzes per exam. So each quiz is 25 minutes. So I can put 2 quizzes together to make an exam. So that's sort of a good representation too of the kinds of questions you might see. Anything on this first qualitative sort of stuff?
Because I was thinking of it more just like as the kind of graph that you have a graph like the picture that you gave us on our.
Yes. Yep.
Yeah, I was like thinking about like which one has.
Yes. Yes. Yep. So you have to count the number of molecules you have, right? And then if we're making a smaller space, that means we need to shift to the side that has the fewer numbers of molecules. And it's only gases. We have to make sure we look at gases. And that's one of those things too. Phases are really important when we consider equilibria, because when you're writing equilibrium expressions, we don't include pure liquids or solids. Okay. All right, so now we start getting into some kind of computation and problem solving. These tend to be the problems that you're going to see here are going to be much more like you see on the quiz, where they're going to sort of be our single skill type things. The questions you're going to see at the end are a little bit more integrative. They might ask you to do multiple things. You might have to do a little stoichiometry with it. You might have to do something that asks you to put some multiple skills together, which is why they're comprehensive problems. Okay, so this problem says, consider the following decomposition reaction. So 2A goes to 4B plus C. And I do like putting generic reactions on there because it's super easy then to make a different flavor of it. And I know I'm not making something that violates something that can't really happen in reality. So especially if you're practicing a lot of those ones online, they'll be the same kind of thing, that they'll be sort of these generic equations. So if B is appearing at a rate of 0.58 torr per minute, okay, and so we want to talk about these gases. We're representing concentrations in terms of a partial pressure change per minute. So remember, anytime we see rate, rate is going to be reflecting a change in an amount as a function of a change in time. So you go ahead and write your rate expression. I'm going to write it here. We'll see if we're the same, and then we'll talk about it. Right, so we have one thing disappearing. So we should have a -1/2 times the change in concentration of A over change in T, and then 2 things appearing. And it doesn't matter what order you write them in, okay? This one actually doesn't even need to be here because this problem is actually asking us to write the rate expression for the decomposition of A and calculate its value. We really don't know anything about C right now, and the problem is asking us about A. So that's why we need to have that A piece here. And because they give us some information about B appearing, that's going to go here. So this part that I have right here is not even necessary for the problem. So if you didn't have it, you know, this wasn't asking us to write the entire rate expression, but that's the part of the rate expression that's going to be important for what we're doing here. Does that make sense? Okay. So now to solve this, what we're going to do is we need to say that this rate of 0.58 torr per minute, we don't need to worry about putting units in because our answer is just going to have the same units. That goes in for this piece. And if we're talking about the rate for the decomposition of A, that's this piece. And this is this really important piece that we still have to keep the fractions. Okay, so what we're going to have is we're going to have 1/4 times a number, and that number is 0.58 equals 1/2 times what we're interested in, which is the rate of change in A, which is the decomposition of A. So 1/4 of 0.58, essentially we're going to multiply that by 2. That's how that algebra is going to work. And you get 0.29 torr per minute equals the change in concentration of A as a function of time. Classic mistakes that students make with these kinds of problems is they forget that they have to keep those fractions. And don't worry about the negative that's here. We're never going to have a rate that's negative. So don't, when you go to solve this problem, you can just get rid of the negatives. We don't need to worry about them there to solve this kind of a problem. Questions? That one's good. So this one says, write the rate expression for the production of C and calculate its value. So here I'm going to write a similar rate expression, right? And we want to find the rate expression for the production of C. And since you could solve this problem either by using your answer from A, so we could write the rate expression of C as a function of A, which we just solved for, or you could use B again. Okay, my answer key just has B here. So we're going to use the same information as we had from above. Okay, so this is going to again be that 0.58 that we have there. And we need to multiply it by a quarter. And because there's no fraction that we have for C, that answer is just going to be 1/4 of that concentration, that the rate change in B. So no fraction that's there. So that our answer is going to be that whole part. Okay, so that's going to be 1/4 times 0.58. So that's going to be 0.145 torr per minute. And if you wanted to be fully accurate, you probably would round that to 0.15 to have 2 significant digits. But always remember, I give you plus or minus 1 significant digit. So that's not an issue. Good question. Good. No questions? All right. So this part is a little bit more involved, but it says if this reaction was carried out in a closed vessel and the partial pressure of A was decreasing at a rate of 43 torr per minute, what is the rate of change of the total pressure in the vessel? So here's how we want to think about this guy. I'm going to write out my equation down here, so it's a little bit easier to think about. 2A, again, is decomposing to 4B plus C. Okay. So it tells us that the partial pressure of A was decreasing at 43 torr per minute. Okay. So we know that C, what do I have here? I'm looking at what I have here. C. Something is not right here. So it should be that we've got, this should be that 4B is increasing at 86 torr per minute, right? Does that make sense why that is? Take into account the coefficients. And C is now going to be increasing at 21.5 torr per minute. So I'm just looking at my key here and something is not right because I have this guy as increasing at 46 and that's not right. So we're just going to go through and do this with the right numbers, and I'm going to have to make sure to put a correction on my key that we have there. I'll have to take a look at my key. I'll do that at the end here when we're all set. What we're going to recognize here is as our reaction proceeds, some of A is going away, but we're making some of B and some of C. So we're going to add 86 and 21.5 together. And I know you got your calculator out. So go ahead and do that and then subtract 43. $64.5. So I think this is why I did it this way. Let me think about this for a second. I think that's got to be right. So my net, I've got to go back and look at my other key here in a second, because I might just have not have it right here. But what's your number that you have? 64.5 torr per minute. And that's going to be increasing because we're having more gas molecules that are made than are going away. So that's consistent. That makes sense that we should have that partial pressure increasing. Because the pressure of the vesicle is the vessel is a function of all three of those gases. And since one of them is going away and then two of them are being produced, it's going to be the net sum of those. But so I got to look at my key. We'll come back to that one. But does that conceptually make sense? I have to find out why my key has something different. Yep. Okay. So let's go through and highlight, just so you know, these are the kinds of problems you're going to see. You're going to see a problem that has you write a rate expression and use a rate expression. So we saw pretty much stuff just like this on the quiz. This guy's a little bit new to think about something like this, but it's really just applying what we had there and saying, let's consider a higher population of stuff. And knowing that partial pressure is the sum of all of those gases, we can take into account what's increasing, what's decreasing, and the net is going to be what's happening overall to our pressure change. Okay.
Products like B and C, are they always going to be ones that you add together and then it's always going to be?
Yep, and that's because these guys are appearing and this is disappearing. Yep. Okay. So moving on to the next page, next set of problems. Okay. We have two problems here, and hopefully when you look at these problems, you're going to see a problem that's going to ask you to figure out how old something is. These are always going to be first order processes when we're talking about like dating something. Okay, so that's always going to be that ln set of equations. And you're going to be solving for one of four things, right? How much, and usually with the dating, you're solving for how much time has passed. But anytime we're using those integrated rate law problems, we have how much did we start with? How much do we have now? The difference of these, which is how much has reacted, or how much time has passed. Okay, there is like that fourth variable, which is the rate constant, but that's usually not something we're solving for with these problems. Make sense? Okay, so this problem says a cotton dress from an Indian burial ground has a specific activity of 12.38 D per min times G. And you look at that and you're like, what the heck is that supposed to mean? Keep in mind when we're doing things with like anything with rate and using an integrated rate law, you might see something that just has some weird units. Remember that those units don't really matter. It's just, and sometimes I call it activity. Sometimes I call it, amount with N. It doesn't matter what the units are. Just if you're talking about amounts, they have to be in the same units. And your answer, if you're figuring out amount, is going to have that unit. Does that make sense? So don't worry about like weird looking units if you see them when you're talking about a rate problem. Doesn't mean you need to do anything with those pieces. So again, this tells us, and when we do carbon dating, they're usually going to be giving us this ratio of normal carbon to radioactive carbon, and knowing that that ratio changes as something, as soon as that organism dies, then that ratio starts changing. But as long as the organism is alive, that ratio stays the same because you're continually replenishing that radioactive carbon. So that's sort of the premise behind how this happens. But here's how you're going to solve these problems. If you see how old is something problem, thing that is a dating problem is going to be first order. That is going to be a first order process, which means we need to use this equation. Natural log of what you start with over what you have now equals KT. So those equations are provided on the front page of your exam, but again, you need to know to grab the one that is first order. Now, if you see a chemical process, okay, the next problem we're going to do is actually a chemical process that could be first order, second order, zero order. And we'll talk about the different ways that you can sort of sleuth through and try to figure out, okay, what order is it so that I know what equation to use. Okay. Now, dating problems usually give you a half-life. Half-life is not part of our equation here. So the other thing that you'll need to use is you'll need to use the fact that our rate constant is going to be equal to 0.693 over our half-life. So that's going to allow us to get our rate constant from our half-life. Now, I do think the equation on the front page of your exam might have these two switched. It might say half-life equals 0.693 over K, but solving for the variable that we want, which is K, you're going to use this flavor of it. Okay. What I like to do with these problems is kind of keep track of all the pieces that we have. So what we start with, okay, and this is kind of the ratio for living organisms. That's going to be how much you start with, 15.3, and I'm just going to call them units because we don't need to worry that it's I think the D stands for disintegrations per minute times gram of substance that you have. Keep in mind, you are always going to have what you start with be a bigger number than what you have at time T. So I think that question came up in class once in terms of making sure you put things in the right spots. You should always have the ln of a number greater than 1. If you don't, probably put stuff in the wrong spot. So that's what we start with. We know what we end up with here is 12.38 units. We know our rate constant is going to be equal to 0.693 over T1/2. Okay, so that's 0.693 over 5,730 years. So that's going to be 1.209 times 10 to the minus 4th year minus 1, reciprocal years. Everybody good? Everybody? Emma, you're the only one here. So Emma is good. Okay. So now we're going to take this guy and we're going to put these pieces in and we're going to solve. Okay. So ln, what we start with, 15.3 over 12.38 equals 1.209 times 10 to the minus 4th times T. And let me actually go in and I'm going to put in my units. So this is year to the minus 1 times T. And that's a reminder that my answer is going to have your units of year. Okay. Now this problem, you don't need to use E for. The only time you need to use E is if you're solving for something that's in there. In this case, we're just going to take the natural log of what that ratio is. Okay, so that's going to be the natural log of 1.23586 and change equals 1.209 times 10 to the minus 4th year minus 1 times T. That's going to be 1751.6. Once I take that natural log of that number and then divide by 1.209 times 10 to the minus 4th. Okay, so that's going to be equal to my T. Rounding for significant digits, my time is going to be equal to 1,750 years. So if we're talking about doing anything that is dating and we're using radioactive decay, things like that, we have to remember that it's first order because it doesn't tell us anything that's doing radio dating is going to be first order. So these then are the equations that we need to use. Those are always going to be our equations for first order processes. Okay. Lots of different flavors for equations. I might ask you for a radioactive isotope that got spilled and it has a half-life of this and you started out with this much. How much is left after this amount of time? Okay, so there's lots of different flavors, remembering that the different pieces we can ask you to solve for, how with, let me go over here to the equations, how much you start with, how much you have now, how much time has passed, or again, the difference between these two is going to not the division, but A sub 0 minus A sub T is how much has reacted. Questions on this guy?
It's just like for dating, it's obviously in the first order, but if you said like radioactive things breaking down, like and those can have different.
Those are always first order. Yep, and that's why we learned, we sort of like learned those in the context of nuclear decay because it's simple. It's always first order. Okay. Now we come down to this guy, okay? Nitrogen dioxide decomposes according to the reaction. So one of the things that becomes challenging for students is they see, oh, decomposition, and they like, that's nuclear decay, and they start trying to do rate stuff. But a few things should be alarm bells that this is not a rate problem. What are they? Yep. We see these arrows that tells us that this is an equilibrium problem. What else? Okay. It's asking, well, it gives us I mean, we see the words equilibrium that are in here, but if you don't see sort of equilibrium that's in here, the fact that we see a big K, that's an indication that we're doing an equilibrium problem. So don't be throwing out equations like this. We're not going to be doing kind of stuff with that. So this tells us we've got nitrogen dioxide decomposing. It gives us a chemical reaction. They give us a Kp value. And they tell us if we've got 0.75 atmospheres of NO2 added to a container, allowed to come to equilibrium, what are the equilibrium partial pressures of the two product gases? So as soon as you know it's equilibrium, you should have those 6 steps in your head. Make sure you got a balanced chemical equation. Second step is write your equilibrium expression. Third step, make sure everything's in the right units. Fourth step, set up an ice table. Fifth step, solve for X. Sixth step, put it back in to answer whatever the question prompt is. Okay, so we're going to go through and we're going to do all of those steps right now. So here's step 1, balanced chemical equation. Step 2, let's write our equilibrium expression. So this is Kp. Okay, Kp is going to be equal to 4.48. Let me actually write it first and then we'll see what it's equal to. Kp is equal to the concentration of oxygen. So we can represent partial pressures by putting them in parentheses versus brackets. Sometimes too, you might see them. I'll show you another way that you can see it, which is totally correct. So times NO, the concentration squared, over NO2, the concentration squared. Sometimes you might see these written as a P with NO. So you might see that like that. That's another way to represent that. That's totally correct as well. And numerically, this is equal to 4.48 times 10 to the minus 13th. Remembering that equilibrium constants do not have units. Rate constants, very importantly, have units that differ and depend on the reaction order. Okay, so now our third piece is make sure that we've got everything in the right amounts. Because this is a Kp, we need to make sure that we've got everything in atmosphere. And yep, they were given in atmosphere, so we're all good there. Usually you won't have to do anything with atmosphere. You also could have things in torr, but we tend to see them in atmosphere. The main time that you're going to have to do something is if you are given the volume of your flask and the number of moles of gas that go in. In that case, you need to figure out molarity by taking the ratio of those. Okay. Fourth thing is now we're going to do our ice table. So to make your ice table, you always have your balanced chemical equation as your top line. Initial change in equilibrium rows. Everything is a gas here, so everything sort of participates. There's not anything that we exclude because it's a liquid or a solid. I should say a pure liquid. So we know that we start out with 0.75 atmosphere of NO2 gas and nothing else. That's important because this is going to tell us which way this equilibrium shifts. It has to shift to the right because we don't have any product. So we're going to have two scoops go away of our reactant, 2 scoops appear of our NO2, and then 1 appear of our O2. So then we got 0.75 minus 2x, 2x, and x. So that's completing step 4. So step 5, there's lots of ways we can solve for x. The way is maybe the problem tells you the equilibrium concentration of one thing. If that's the case, you set it equal to that one thing. So if I told you what the equilibrium concentration of NO2 was, that number is going to be equal to this. You solve for your x that way. And then you can use that x, step 6 is then figure out how to answer the question prompt. I could also tell you not the equilibrium concentration of one thing. In this case, maybe I could tell you what the partial pressure is of all of the gases. Then that number is going to be equal to the sum of all of these. Then you still solve for X and then put it back in. So sort of the easiest way to solve for X is you get one of the equilibrium concentrations. And that tells you then how, if I told you the equilibrium concentration of O2, I'm telling you X directly. Okay. If I tell you the concentration of NO2, you just divide by 2 and that'll give you X. Okay. This problem is not like that. We aren't given anything. So how you normally would solve for X in that scenario is you have to take these variables and put them into your equilibrium expression. That's always how you solve for X. So that's the 5th step. So we're going to have our oxygen concentration, which is X, our NO concentration, which is 2X, but we have to remember to square that whole quantity. That's a common place students make mistakes, is they don't square the whole quantity. And then 0.75 minus 2X, square the whole quantity. Now this is going to become problematic if we can't do something to make this a little simpler, because we're going to have 4X cubed in the top. We're going to have X squared and X's and constants in the denominator. That's a pain in the butt. So this is where we have our simplifying assumption. Okay, so we're going to say that we're going to assume that X is small, and you can just write assume. But when we assume that X is small, this simplifies so that we've got 4X cubed over 0.75. We still have to remember to square that 0.75. And then that's going to be equal to our equilibrium constant, which is 4.48 times 10 to the minus 13. Now, you probably know just looking at this problem that my scoop is going to be really small because I have a very small equilibrium constant. But right now, for this last quiz that we had and for this exam, you still need to prove to me that that's okay. You can do a pre-check beforehand, which we didn't do here, but we'll show you how to do the post-check afterwards. Okay. So go through and solve this. I'm not going to go through the details of the algebra, but just to sort of walk through it, square 0.75. Okay. And then you're going to multiply both sides by 0.75 squared. Okay. Then you're going to divide by 4 and then take the cube root. Reminding people an easy way to take the cube root, if you don't have it on your calculator, is you're going to take it to the 1/3 power. So there'll be, you should have a little caret symbol, and then you can put in 1/3 power in your calculator. So solving for X gives us 3.98 times 10 to the minus 5th. Okay. Now we know our units here in our table are going to be atmosphere. Okay. So that's what our X is. It's going to be atmosphere. So we need to go and then put in, this problem asks, what are the partial pressures of O2? Okay. So that partial pressure of O2 is equal to X. And so that's going to be 3.98. That does not look like a 9.98 times 10 to the minus 5th atmosphere. And then the partial pressure of NO is equal to 2X. And that's equal to 7.96 times 10 to the minus 5th atmosphere. Now, sometimes things that students want to do is they still want to like somehow square that thing on the bottom as well. Don't get square happy, right? We're not going to square that. We're just doubling it to get our answer here. Now, one of the things that's kind of cool is if you wanted, this problem didn't ask you to solve for the concentration or the partial pressure of NO2, but if you solved for this guy, you'd essentially have 3 numbers, okay, that you could put back into here, I should say back into here, and you should get back close to this number. So that's a way that you can check your answer on an equilibrium problem. I wouldn't spend time doing it while you're doing the test, but if you have time at the end and you're like, I want to double check and see if my answer is right, you can put in, if you get values for all 3 of those, you can square the ones that need to be squared, and you should get close to, now if you had to make an assumption, it won't be exact, but you should be in the ballpark of 4.48 times 10 to the minus 13th. And that's a good confirmation that I did that right. So that's not something you have to do, but something that you do have to do with these problems early on is you have to do a check. You have to prove that it was okay to make that assumption. So two ways, again, that you can do this assumption. You can do a pre-check or a post-check. Okay. So if you want to do the pre-check, what you're going to do is you're going to take your amount that you start with and divide by your equilibrium constant. And that has to be greater than 400. And we didn't do that one yet, so I'm not going to do the math for that. Or you can do a post check. And the reason it's a post check is you have to take your X value and you're going to take your X, okay, and you're going to divide by the amount that you started with. Multiply that by 100, and that has to be less than 5%. So if you do this, you'll actually, we take 7.9, and you actually want to take, in this case, we had a situation where we had something that was a double scoop. So we want to make sure that because we assumed that the double scoop was small. So we're going to put that number, and even if you put X in with this problem, it would still be okay. But in general, you want to say whatever size scoop you're saying you're ignoring. We're saying a double scoop we're ignoring. So we'd put 2X, which is this number, over the amount that we started with, 0.75, okay? Multiply by 100, and you actually get 0.01%. So this is going to be 0.01%, so way less than the 5%. So that's okay. Questions on that guy? Good? Okay. So kinetics, equilibrium, they're intentionally tested together because it's important that we know the difference between when you're doing stuff with like integrated rate law and those kind of equations, and then times that you're doing ice tables and things like that. But we sort of talked about in the beginning, here's tricks how you know that it's equilibrium. Here's tricks how you know that it's rate. Okay. Now, here's a problem when you see a table of data that talks about different experiments and you're changing concentration, you should be saying this is kinetics, method of initial rates. Okay, so you're going to see a method of initial rates problem. So this problem tells us that we're doing chemistry, the bleach ion, so hypochlorite. You guys actually did stuff with that in lab, that you use that to kind of bleach a dye. So this is reacting with iodide and it's forming some other products here. And we determine the initial rate of this reaction experimentally. And we have these three sort of experiments. Okay, so when you see stuff like this, it's generally going to be asking you to determine the specific rate law and the rate constant. And then here's an extra piece down on the bottom. Once you have your specific rate law, you can figure out the rate with any given concentration. So we're actually going to then solve the rate law for rate. Okay, so you're going to see a flavor of this problem. You're going to have to figure out which equations that you want to use to compare. So when you're doing a problem like this method of initial rates problem, first thing that you want to do is you want to write a generic rate law. So rate equals rate constant times the concentration of species raised to powers that are orders that we have to figure out sort of experimentally. Okay. So to figure out experimental orders, okay, we have to figure out where do I have concentrations that are changing and where do I have ones that are held constant. So for example, if I compare 1 and 2, okay, so 1 versus 2, okay, and I know this is a place where students can get confused, like what is the order that it is telling me? If I'm comparing 1 versus 2, I'm holding I minus constant and I'm changing OCL. So 1 versus 2 is going to give me the order for OCL. You see that? So 1 versus 2 is going to be the order of OCL minus. Okay. And now if I compare 1 and 3, Okay. 1 and 3, I am holding OCL constant. And then I'm changing I minus. And so 1 versus 3 is going to give me the order of I minus. Okay. So what we need to ask is what's the fold factor in rate and what's the fold factor in concentration change. So I'm going to write my C's and my R's here. So let's take 1 versus 2. Okay. So if I'm comparing 1 versus 2, there's going to be 1 versus 3. So 1 versus 2. Okay. Hopefully you can see that the reaction rate is doubling. Okay. And 1 versus 2, I can see that my concentration is doubling. Okay. So my concentration is doubled and my rate is doubled. Just like we did this qualitatively on the first page of the exam, I can see that this is going to be something that it's first order for OCL. Okay. So it's going to be first order. Now, we could easily do this math in our head. It could be something that you may need to do a little calculator work to actually get what these numbers are. All you need to do is take and divide the larger number by the smaller number. One of the things I saw on previous quizzes is sometimes students would take this number, like reaction 2 and divide by reaction 1 for rate, but then they take 1 and divide by 2 for concentration. And so you have to make sure that it's always the same. And you could do it either way. I work better with numbers greater than 1 than numbers less than 1. So I always like to take the bigger number and divide by the smaller number. Okay. We do the same thing when we have our 1 versus 3 here. For 1 versus 3, we can see that concentration fold is doubling. Okay. And so I can see that my rate is also doubling. So it's also first order with respect to I minus. So what that's going to allow us to do is write a more specific rate law, which is rate equals rate constant. Now it's going to look kind of the same, but my M's and my N's now are going to be 1. And we, by formalism, don't write them in there. Make sense? Now, once we know our specific rate law, where we now know those reaction orders, we're going to solve it for K, and we can use any of the experimental data. So I'm going to use reaction 1 here. You can use any of the reaction data, but by using data from reaction 1, I'm going to solve my rate law for K. So my rate is going to be equal to, well, let's write this down. So we're going to have rate equals rate constant times OCL minus times I minus. Okay, so I'm going to put my value in for rate. So it's 1.36. And be very careful when you're doing this to watch your units, because the units of rate constant are really important. Okay, so rate always has units of concentration per time. In this case, it's molar per second. I'm going to be solving for my rate constant, and then I'm going to have 1.5 times 10 to the minus third molar and 1.5 times 10 to the minus third molar. Okay. Numerically, I'm going to get 60.44. But if I think about what I'm going to have for units here, my rate is going to have units of molar per second. And then I'm going to put in my denominator 2 more molars. You see that? So now one of my molars is going to go away. And this second really can be in the denominator. So my units are going to be reciprocal molar, reciprocal second. So writing the correct units for your rate constant are really important too. Okay, good. All right. So now the last piece is, once we know all of these pieces, now we know our very specific rate law. We know that rate equals 60.44 molar per second times the concentration of OCL times the concentration of I minus. That is the super specific rate law. Now we're going to solve for rate. That's what this problem is asking us. It's like, what is the reaction rate? So now we're going to solve for rate, putting in information that's provided. So they tell us that the OCl concentration is 2 times 10 to the minus third. And they tell us that the I minus concentration is 5 times 10 to the minus fourth. So all we're going to be doing is multiplying those pieces together. Okay. And we'll notice that we're going to get the right units here for rate, but let's just go ahead and check. We've got 60.44, and I'm just going to put molar and second in my denominator there. And I'm going to multiply by 2.0 times 10 to the minus third molar. Then 5 times 10 to the minus fourth molar. Okay. And what I can see, canceling out my units, one of my molars is going to go away, and I'm left with units of molar per second, which is the right units we always have for rate, concentration per unit time. So math for this, rate equals 6.0 times 10 to the minus fifth molar per second. Good. All right. So you're going to see a method of initial rates problem, and you're going to see these pieces that sort of build on one another. Now here's a problem, right? Use your deductive reasoning skills. Hey, I've got these things that tell me, again, this is an equilibrium problem. I see equilibrium arrows. I see big K values. Okay. So this problem actually walks us through kind of a Q versus K comparison, kind of some qualitative stuff that we're going to have here. And then we're doing a Q versus K comparison. And then we're going to do a Kp versus Kc interconversion. Okay, so you're going to see a flavor of this, which kind of mixes qualitative and quantitative pieces. So initial concentrations of all species are as given here. Calculate the value of QC. So remember, if we're writing QC, we'd write it the same way we wrote Kc, which is products over reactants. So we've got C2H5OH. All of these are gaseous species, so they're all going to appear here. So we've got C2H4 times H2O. I'm going to put the values that were provided here, right? So we've got C2H5. This is ethanol, so that's going to be in my numerator. I've got this guy in my denominator and my other guy here in my denominator. Nothing is squared or anything here, so it's just going to be these numbers. And I get 3273.8. If I kind of round this, I'm going to get around 3,300 is what my Q is. Remember, Q represents where you are at. Okay. And then K represents where you want to be. So asking a qualitative question, will the reaction move towards reactants or products to reach equilibrium? You have to do a Q versus K comparison. So in this case, we've got about 67,000, right? 67,000 is what we're going to have. Actually, it's 670,000, sorry, 670,000 is what we have for our K. So in this case, Q is less than K. Okay, and when Q is less than K, what that means is reactants, or the reaction, I should say, reaction moves towards products. So if you want to find out which way a reaction shifts, you need to say, where am I at versus where do I want to be? Q versus K comparison. If Q is less than K, you keep marching forward. If Q is greater than K, you got to go back towards reactants. Okay. value for Kp. This is where we need to use this equation that says Kp for interconverting Kp and Kc, Kp equals Kc times RT to the delta N gas. Okay, we need to figure out how many moles of product gas, subtract the number of moles of reactant gas. Okay, so if we think about what we have here, we've got 1 mole of reactant gas, and we've got 1 mole of product gas, 2 moles of reactant gas. So our delta N is going to be equal to -1. That makes sense? Okay, so delta N is going to be equal to -1. Okay, so we're going to use that here. Kp is going to be equal to the Kc value is what was given. Now, if we needed to interconvert Kc and Kp, the only thing that differs is this would be a minus sign that's there. Okay, both equations are going to be provided for you on the front of your exam, but if you needed to go the other direction, you'd actually take the negative of your delta N gas.
But if it was the other way, it was Kc, and it was, negative delta N gas. But then we have a negative already, would it just become positive?
Yes.
Okay.
Yep, good question. So if this was this equation and it had a minus up here, -1 is +1. Yep. So Kp is equal to Kc, which is 6.7 times 10 to the 5th. We need to put our R and our T in. So R is 0.08206 liter atmosphere per mole Kelvin. Now you're going to see, I think there's 2 R values that are on your, on the front page. You need to know which one to use. Units are going to help you here because we're doing stuff with gases. So you're going to want to see the ones that's liter atmosphere mole Kelvin. The other one has units of energy. We actually haven't really used that one yet. So that's not the one you want to grab. Constant provided for you on the front page. Okay. Yep. But there's going to be 2 values for R. You have to make sure to grab the one that has to do with gas stuff. Another one is it's going to be 8.314 joules per mole Kelvin. It's going to have units of joules and energy, and that has nothing to do with what we're doing here. Okay, so we're going to have this guy multiply by temperature. It tells us 350 K, just coming up to the top here so that we can see. It tells us that we are at 350 K, so that's where we get this piece, 350 K. Okay, we haven't really learned the how or the why or why it's important. This will be a Gen Chem 2 piece. Rate constants are temperature dependent, which is why that temperature piece comes in here. And importantly, we need to have this to the -1 power. Okay, if you don't know what it means to put something to the -1 power, it means it's in the denominator. Okay, so we're basically going to be taking and multiplying those 2 things together and then taking 1 over that number. A lot of calculators will have a -1 function, and then we're just going to multiply that by 6.7 times 10 to the 5th. What we end up getting is Kp is 2.3 times 10 to the 4th. So that's what you'll get for that answer. Okay. Last thing, asks us to think about how we manipulate reactions. So it says using your results from above, calculate P for the reverse reaction at this temperature. So when we reverse a reaction, okay, K becomes 1 over K. So we need to take 1 over. So if it was a reaction that very much favored products based on what we see from this K, because it's a large number, going in the opposite direction means it should be a very small K. And we're going to see that when we take 1 over a large number. Okay, so 1 over 2.3 times 10 to the 4th equals 4.3 times 10 to the -5th. Nope, we do not have units for equilibrium constants. Rate constants, units are super important. We do not have units for equilibrium constants. Good, questions? Okay, so that wraps up the kinds of questions that everybody is going to have to do. So just kind of refreshing, we're going to have equilibria with sort of Q versus K comparisons and shifting. method of initial rates, a problem dealing with ice tables and kind of either type 1 or type 2 kind of problem, and then an integrated rate law problem. Okay, and then we've got sort of a rate expression type problem. There are 2 problems at the end, and I've got 2 examples here. One, and these are called complex problems. They're only worth 15 points out of the total 150. So don't freak out if it's something that you're like, I didn't have time to really do it really well, or I didn't know how to do either of them, or I only got through part of it. It's 10% of your total grade, so not a lot. So don't freak out. I would definitely save these till the end and you feel confident with everything else you have. You only pick one of them. You're going to tell me which one that you want to do. One of them is a rate problem. One of them is an equilibrium problem. So you're going to pick the one sort of that you're most interested or feel the most confident sort of doing. So let's do problem 10 first. Okay. So dinitrogen pentoxide decomposes in chloroform as a solvent to yield NO2 and O2. So we've got an equation here. So this is the type of a problem. You have to have a balanced chemical equation. It doesn't really tell you what that balanced chemical equation is. So let's start writing this down. And I'm going to highlight, I'm just going to cross this off here. We're not doing 11 right now. We're doing 10. So this is problem 10. Next page, we'll do 11. So dinitrogen pentoxide, and I didn't even write the right thing here. I'm speaking and saying, so N2O5 decomposes in chloroform as a solvent. So we don't need to worry about that. It's just telling us it has to be in a solution to generate NO2 and O2. And just writing this, we can see that it is not a balanced chemical equation. If you go through and figure out what you need to have to balance it, you're going to get 2 and a 4 there. So that's what we're going to have to balance this chemical equation. The decomposition is first order with a rate constant as given there. And this should be, indication that this is the kinetics problem, right? We're seeing information about first order stuff. So that's the kinetics problem. We've got a rate constant that's provided. It says calculate the partial pressure of oxygen produced when we have 1 liter of this concentration of N2O5 at 45 degrees over a period of 20 hours if the gas is collected in a 10-liter container. There's a lot of information that we kind of have there, but it's talking about probably doing something with amounts. So we should be having, and if you're struggling with like, what do I do with this problem? Okay, it's kind of asking about amounts. It's a rate, it's a kinetics problem. Let's see if we can work through. Let's start with using our integrated rate law and see if we can start getting pieces that allow us to put things together. So first order kind of rate law tells us, well, let's see about doing this ln of A0 over AT. And I don't need to have my concentration pieces here. So let me just erase those. Didn't want to erase the whole thing. Oh, I guess it would. They're touching one another. Okay. ln of A sub 0 over A sub t equals KT. That's going to kind of be those pieces. That's that equation. Okay. It actually gives me the rate constant. So I don't need to use that 0.693 over T1/2. It actually gives me the rate constant. Okay. So let's see if we can kind of work through what we have here. So we've got some pieces that we have here. A sub 0. Now we need to have amounts in concentrations. So we have 0.600 moles in 10 liters. And I'm looking at this and there is a typo in this. This should say, hang on a second. No, there's not a typo. Sorry. I just can't read my writing. Okay. So we take a liter of a 0.6 molar solution. Okay. So let's start kind of with that piece. We talk about what we have with our N2O5. Okay. We start with 1 liter of a 0.600 mole per liter solution. So that tells us that we've got 0.600 moles of N2O5. Does that make sense? Okay. So now what's going to happen is we are going to have everything in a 10-liter container. Okay. So we start by kind of figuring out, well, we're going to take 1 liter of this gas to start. And so that tells us that we've got 0.6 moles. And then we're going to be having it in a 10-liter container. So that means that our N2O5 is going to be 0.600 moles in 10 liters. So that's going to be 0.06 molar. Okay, so that is going to be sort of our starting concentration of that species. With me? Okay. So again, writing down what we have, A sub 0, what we start with, N2O5 is going to be 0.06 molar. Now A sub T, let me flip up so we can sort of see here. It says calculate the partial pressure of O2 produced when we have this. So we're going to be having some of this kind of break down. So we're going to have to figure out how much N2O5 sort of breaks down, and then we're going to use stoichiometry to relate that to how much O2 is produced. So even though this is weird, because we normally don't necessarily think of doing kinetics problems by saying and talking about products, because we know stoichiometry, if we can figure out how much N2O5 reacted, that can tell us how much O2 reacted, because we're going to make half as much O2 as we reacted N2O5. Does that make sense? All right, so A sub T is going to be something that we're interested in. We know how much time has passed, okay? So they told us 20 hours has passed. And then our rate constant is going to be 1 times 10 to the minus 5th per second. Okay. With me so far? So when you have problems like this, especially if you see it's the kinetics problem, if you didn't know where to start, all right, told me it was a first order process. So I'm going to have these pieces here and figure out, okay, I know how much I start with. I know how much time has passed. They gave me rate constant. I must need to do something with the amount that's left. Or as we're going to see, it's the amount that's kind of reacted. Okay. So red flag that should be here is the fact that we see that the time that's passed has units of hours, but our rate constant has seconds. So, and a lot of people got in trouble with this on the kinetics quiz, that they tried to change the units of the rate constant. You can do that, but it's easy to get mixed up because they'll try to say, oh, I know that there's, they'll put seconds in the denominator. Like they'll be like, hey, there's 1 minute is 60 seconds. 60 minutes is 1 hour. And but nope, that seconds is in the denominator. So I always tell people you are better off going and changing your time and knowing that 1 hour is 60 minutes and 1 minute is 60 seconds. And I get 72,000 seconds. You're better off changing your time rather than your rate constant, because it's super easy to get those mixed up. Okay. All right. So now what we're going to do is we're going to solve this equation for A sub T. Okay. So I'm going to have the natural log of what I start with, 0.06 divided by what I end up with, A sub T, equals my K, which is 1 times 10 to the minus 5th times my 72,000. I'm going to move my stuff over here a little bit. With me? Now, this is one of those where we're going to have to use the E because we're solving for something that's part of the ln fraction. Okay, so we're going to have e to the, that side, equals e to the, and if I multiply those two numbers together, they're going to end up being 0.72. So 72,000 times 10 to the minus fifth is going to be 0.72. So now I'm going to have 0.06 over a sub t equals 2.0544. And I'm kind of like all over the place here. So let me just move this down. A sub t is going to be equal to 0.0292 molar. Okay. With me so far? Okay. So telling me how much is left right now does not allow me to do stoichiometry. I need to know how much has reacted. Okay. So see if this makes sense with what we're going to do here. I know that I've got 0.0292 moles per liter of N2O5 that are left. Oops, and I should put, sorry, this in the denominator because this is the concentration. Okay, so that's how much is left. I know that it's contained in 10 liters. So that tells me that I've got 0.29205 moles of N2O5 that are left. With me? Okay. I need to go on to, and just because I was doing so much writing and talking and explaining, I got to put a little blank piece of paper here to kind of finish this guy out. Okay, so I know that I had 0.600 moles of N2O5 initially. You see where that came from? So I'm going to subtract the 0.29205 moles of N2O5 that are left. And that tells me that I had 0.3019 moles of N2O5 that are used. And this is important because I need to know the amount that was used if I want to do anything with stoichiometry, which is going to allow me to change who I'm talking about. Right? That's an important piece of stoichiometry, is changing who I'm talking about. So I'm going to go and I'm going to copy my equation back here, just so I have it up top here. Okay, so if I've got this equation, I can say if I've got 0.3019 moles of N2O5 that were used, I can use my balanced chemical equation. 2 moles of N2O5 reacted will produce 1 mole of O2. That will tell me that I produced 0.15397 moles of O2. Make sense? Okay. Now the problem is asking, what is the partial pressure of O2? Do you know a way that I can convert the amount of oxygen produced to a pressure? If I knew, for example, the volume that it was contained in, and I knew the temperature that it was at, and this is at 45 degrees C. I'm going to pick a new color because this is really important. How about that equation? That's why this is a complex problem, because it pulls in sort of multiple pieces. So if I have partial pressure, if I know the quantity of gas, the R gas constant, the temperature that we're at, and the volume that that gas is contained in, I can figure out the partial pressure. Okay. So let's put our pieces in. We just figured out the number of moles of gas. Our gas constant is that 0.08206 liter atmosphere per mole Kelvin. The temperature, I need to make sure to convert that to Kelvin. So this is going to be 318 Kelvin. Do you remember how to convert Celsius and Kelvin? Add 273. Yep. So that's going to be 318 Kelvin. And then I divide by the volume. This was all contained in a 10-liter flask. So it's 0.402 atmosphere. That's a problem. That is a problem. Okay. So it asks us to combine, just kind of reviewing it. We're going to use, it's a kinetics problem because we're going to ultimately use a first order rate equation to tell us how much we have left. Once we figure out how much we have left, we can then figure out how much we reacted by taking the difference, because how much we reacted is going to be important to change who we're talking about and find out how much product we produced. And then the last little piece is bringing in a skill from before. It's like, hey, PV equals nRT. That's going to allow us to figure out the partial pressure.
It's kind of hard to believe that that's all contained in 10-liter flask.
Yep. All right. Last problem. And then we have run longer than the hour that I anticipated. So let's do our equilibrium problem. Okay. An industrial chemist introduces two, and again, equilibrium problem. This should be like, hey, this is the equilibrium problem. Okay. An industrial chemist introduces 2 atmospheres of H2 and 2 atmospheres of CO2 into a 1-liter container at 25 degrees C, and then raises the temperature to 75 degrees C. And at that temperature, remember we said equilibrium constants are temperature dependent. That's what our equilibrium constant is, 0.534. Okay. We want to know how many grams of H2 are present at equilibrium. Okay, so equilibrium problem. So let's go through our steps. First step, make sure we got a balanced chemical equation. We do in this case, we didn't have to worry about creating it. Okay. Next step, write your equilibrium constant. Okay. So we've got Kc is equal to, we're going to have the concentration of CO times the concentration of H2O over H2 times CO2. Okay. Oops, I should have written Kp. That's my fault. Sorry. And I should have probably had parentheses here. So let me fix those. Kp, right? Because we got everything in atmospheres. So we're going to have these in parentheses. You wouldn't get that wrong if you had it the other way. Okay. We need to make sure that everything is in the right units. And that's, as I was moving on to this next step, I was like, oh, Dr. Parenti, not right, because Kp is going to be atmosphere, and we're okay there. Oh, that's why. It does tell us Kc, okay? Yep, but take a look at this. How many moles of gas are on the reactant side? 2. How many moles are on the product side? 3. I'm sorry, 2. So delta N is 0. So when delta N is 0, Kc equals Kp. So you didn't need to worry about doing anything with that. Okay, so even though it gave us Kc, and that's why I wrote Kc, Kp and Kc are equal because delta N is equal to 0. Okay, next step, write our ice table. So we've got H2 plus CO2 goes to H2O plus CO. They tell us amounts that we have. We start with 2 atmosphere of each, none of the other. minus x, minus x, plus x, plus x. All our stoichiometry is nice and simple. Okay. Solving for x. Solving for x is always going to be putting our Kp value is 0.534. So my CO and my CO2 are both x. And then I've got 2 minus x and 2 minus x. So this is a problem. Can I do simplifying assumptions here? Why not?
What is not that low?
Mm-hmm. So the problem is this is too big to do simplifying assumptions. So too large to assume. So this would have to be one of those like quadratic equation things, except I can square root it. Very good. I can do a simplifying algebra. Okay. Doing simplifying algebra is going to allow me to take the square root of both sides. Let's do a different color here so we can see what's going on. Simplifying algebra, take the square root of both sides. Okay. And so now that is going to get me to take the square root of 0.534, 0.7307. This is usually something that stymies students for a little bit. When you take the square root of a number less than 1, you actually get to something greater than 1, which can be confusing. You think you did something wrong in your calculator, but you did not. That's equal to x over 2 minus x. Okay. Again, just walking through because I have it here. When you're solving this, how to solve this is you're going to multiply both sides by 2 minus x. So I'm going to get 1.4608 minus 0.7307x equals 1x. And so I'm going to combine my x terms. So I'm going to add 0.7307x to both sides. So I'm going to have 1.4608 equals 1.7307x. I divide both sides by 1.7307 and I get 0.844 equals x. So that was my 5th step, was solving for x. 6th step is answering the question prompt, which in this case, it says, how many grams of H2 are present at equilibrium? Well, let's figure out what we have. Okay, my H2 concentration is going to be 2 minus x. So H2 concentration is 2 minus x, and that's going to be 1.156, but the units of this are atmosphere. Okay, this asks for how many grams. Do we know a way to take the amount of gas as atmosphere and convert it into grams? Let's say if you knew the volume of the gas, which was, what did they tell us? A 1 liter container, and the temperature of the gas, which was 700 degrees C. PV equals nRT. So PV equals nRT can get us to N, but we have to remember that N is in units of it's gonna be moles. It's gonna be moles. And then we'd have to do one more thing to get to grams. Okay. So PV equals nRT, yes, is again our magic equation. So again, if we're solving for quantity, PV over RT is going to be equal to N, but we have to remember that that's going to have units of moles. And as long as we keep kind of our units with things as we're going through our equation here, we're going to be able to see that. So my pressure is 1.156 atmosphere. That's what we just solved. So 1.156 atmosphere. So highlighting where we got that from, this piece came from here. 1.156 atmosphere. We know we're in a 1 liter container. Just highlighting it. It told us this up here, right? We're in a 1 liter container. Divided by that R is the same R, 0.08206. liter atmosphere per mole Kelvin. And again, that mole Kelvin is why we're going to have units of moles in our answer. Our temperature was 700 degrees C, which once we convert that to Kelvin is 973 Kelvin. Okay. We're going to have N equal to 0.01448 moles of H2. Now I can do a little bit of unit conversion, 0.01448 moles of H2 times 1 mole of H2 is 2.016 grams of H2. So I get 0.029 grams of H2. All right. So a theme maybe to see here and to think about is we're doing a lot with gases right now, and we learned about gases before. So PV equals nRT is an important way for us to interconvert quantities of gas. Now, keep in mind too, you would not be doing both of these problems. So it took us a little bit of time to work through everything here, but you would be choosing one of these problems, either the equilibrium problem or the kinetics problem. But I might think that you're going to see something that involves having to use PV equals nRT in some capacity. Questions? That was a lot. Now, keep in mind, we did a lot of discussion and explaining and all kinds of stuff here. So even though this was way you'll have for the exam, it shouldn't, first of all, because we did 2 of the longer problems, the exam is designed to be done in your 50-ish minutes. Questions? All right. Good. Good. I'm going to end this.